Okay, so the last bit of the task is to now write some code for computing accelerations using this little vector library that we just defined. So the point of what we just did is that we created this domain-specific library for talking about points and vectors. And so now we can use that in the code we're going to write down here. So the first thing we have to think about is, how do we represent a body? And what we said back at the beginning of this whole story was that for a body, what we need to remember is the mass, the position, and the velocity. So we'll say that the type body is a pair of a mass, a position, and a velocity. And now we have to think about how to represent each of those. Well, the mass is just a number, so that can be a number. The position of a body in space is a point, and the velocity we'll do as a vector. And I've copied in my gravitational constant here. So now, remember, we were defining before, like aij is the acceleration on body I to body j. And we said that the formula is that a ij is equal to g times mj divided by d squared, where d is the distance from I to j. And that's what that's actually doing, is it's describing the magnitude of the acceleration. And then the direction, we said the convention is going to be that it points we want the acceleration on body I due to body j, then it's going to point from I to j, because if it's the acceleration on body I due to j, then it's pulling from, if it's the acceleration on Earth due to the sun, then it's pulling from the sun towards the Earth. Okay, I think I got that right. Okay, so really our purpose then is to compute the acceleration aij. Okay, so how should we design this function? Well, let's call it the acceleration on, and it's going to take in mass 1, position 1, velocity 1, which is a body, and mass 2, position 2, velocity 2, which is a body. And what should act on return? Well, it should return an acceleration vector. Okay. And first thing we're going to do is we're going to ask if P1 and P2 are the same, then we're just going to say that the acceleration is 0. And I think we forgot to define our 0 up here. Yeah, we did. So it was in my wish list, but I forgot to define it. So what's the 0 vector? Well, it's just going to be the origin. So the 0 vector will be the pair 0, 0. Okay, so why do we say if the two things collided then 0? Well, number one, the simulation that we're using doesn't really work for collisions, because like we're just taking into account gravity and not like the force of things bumping into each other. So like the math would have to be different, right? We'd need a much more complicated physical model there. And the other thing is that if we do this, this will rule out calculating the force of a body on itself, which we don't want to do but when we get down to the calculations down below. Okay, so with that check out of the way, now the thing is to kind of type in this bit. Okay, so how do we start? Well, basically I need to define, first of all, D, and D is supposed to be the vector that goes from body I to body J. And so remember we have this, let me change my notation so that it matches the math a little better. Okay, so remember we have this operation of dash dash greater than up from our vector library, which was the vector between 2 points. And so we can use that to get the vector from I to J. And then if we want to talk about, let's call that Dij, if we want to talk about the D that's in the formula up here, what that D is when we're talking about computing the magnitude as like just a regular scalar quantity, what that is, right, if I wanted to write that sort of like I did on the whiteboard before, then we're putting a magnitude of D there. And so D, let's write it exactly like the code, the denominator of it is the magnitude of Dij. And so we can call that D. And so then we could say that like the magnitude of the vector we want is our G times mj divided by D squared. And so then overall, now what we want to do is, remember the overall formula was the unit vector from I to j scaled by aij's magnitude okay. And so what we do is we take the unit vector from I to j and we scale it by a's magnitude. Okay, so the point is that like once we've got a nice library for working with vectors, the math says that the vector aij is the acceleration on body I due to body j. The magnitude of that is g times the mass of body j divided by the distance from I to j squared, where distance from I to j is the magnitude of the distance vector from I to j. And then we want the direction from I to j be pointing from I to j, which means that we take the unit vector from aij and then scale it by that. Okay, well that just turns right into code, right? We take the distance vector from I to j is the displacement between the position of I and the position of j. The distance quantity is the magnitude of that. The magnitude of the acceleration is g times mj over d squared. And then we can take the unit vector in the direction we wanted and scale it by that. Done. Okay, and so now the last bit is to put this all together. So given a sequence of bodies, so we'll think of that as like A1, A2, A3, dot, 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 dot. What we want to do is compute the bodies B1, B2, B3, compute the accelerations AI for each body BI. Okay, so what we want to get out looks like A1, A2, A3, dot, 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 which is the acceleration on each body. Okay, so overall, in order to take the next step of our simulation, what we need to know is we need to know for each body, the sun, the earth, the moon, Mercury, Venus, Mars, etc. We need to know the acceleration on that body. So how do we do that? Well, we can define a function, accelerations, which is going to take in the bodies, which is going to be a sequence of bodies using the sequence type that we talked about last time. And what we're going to produce is then a sequence of vectors. And the reason we're producing a sequence of vectors is that we've got, for each body, B1, B2, B3, that corresponds, generates a corresponding acceleration A1, A2, A3. Okay, so how are we going to do this? Well, if you're spitting out one thing for each body, right? I'm turning the body B1 into an acceleration A1 and turning the body B2 into an acceleration A2. That looks like a map. So what do I do for each body BI? Well, now I need to figure out the acceleration on the body BI. And what did we say the acceleration on the body BI was? We said it was, if you go back to the first segment of the videos, we said that, second segment of the videos, what we said was that the acceleration on the body BI was the sum of the accelerations on that body due to all of the other bodies. So what we can do is we can take all of the other bodies and map a function that sends body j to the acceleration on body I due to body j on the bodies. Okay, so what this is doing is it's saying for every body bi, for every other body bj, I compute the acceleration on the first one due to the second one. Okay, and so then what I need to do then is add that all up. Well, how do I add up a bunch of things? I do a seek.reduce. What do I need to give reduce? I need to give it the base case, which is going to be the zero vector, and the way to combine things, the way to add things, which is going to be if you give me acceleration 1 and acceleration 2, then I'm going to combine them by doing the vector plus of a1 plus plus a2. That is, I add the vectors there. And then that's my code for accelerations. All right, so let's read it. So what we're doing is we're saying for every body bi, I want to know the acceleration for that body. So what I do is I sum over all the bodies bj, the acceleration on bi due to bj, and then I add all of those up using vector addition. Okay, which, once upon a time, way back in the beginning, we wrote something that was like the sum over j is the sum over j of aij, right? So that was like our ultimate thing there. And that's, exactly what the code looks like here, because for each I, body bi, we're computing this stuff is AI, and it's defined as the sum as vectors now. So like the fact that we're doing the sum as vectors means that we don't have to like separately figure out the magnitude and the direction. We can just sum up all the vectors. And then we get the sum over vectors of all of the AIJs, and the AIJs are written in the code as the acceleration on body I due to body J for every other body in the bodies. So by having a nice library for vectors and a nice library for sequences, we can naturally write this kind of code that processes a whole sequence of bodies by turning each body into the acceleration on that body due to all the other bodies. Okay, so last bit is what are the work and span of this. So the work, basically we can think of it as, remember for map, what we do for the work is we add the work of all of the instances of the function. So what we're doing here, if we look at acon, you can see that acon is all order 1 constant time because it's just doing a bunch of vector operations. And if we page back to all of our vector operations, they're not like recursive or anything. They're just doing like a bunch of arithmetic, because we have fixed size vectors there. So acon is constant time, which means the first thing we can say is that the inner map is order n work because this inner map is mapping a constant time function on, if we, assume that we're doing n bodies, then we're mapping a constant time thing on constant time function on n things, and so that's that. And so then the reduce is adding up n vectors, and so that's going to be order n because if we add up n things, and each addition again is a vector operation, and all of those are constant time, 0 is constant time. So it's a reduce of constant time stuff, which means it's just proportional to the length of the thing you're reducing, which is the same as the length of the map that comes out here, which is the same length of bodies, which is okay. So, which is to say that the inner map and the reduce are order n total together. And so if we do that for each body, then overall, we're looping something that's order n times, and we get n squared. Okay, so now for the span, it's a little bit more fun because when we do the span and we do a sequence map, remember the whole idea of sequence map from last class is that sequence map adds no overhead to the parallelism. So sequence map is just taking the max of the inner functions, which means you just ignore the map and think about like how long does the longest one of these take. And so it's really just proportional to that. And so then here, the sequence map here is free. We just think about how long does the longest one of these take. That's still a constant time. And so really the only thing that counts is the reduce. And if we're reducing a constant time function with 0, then it's just proportional to the log, because reduce, remember, works on a tree and does like our tree addition thing. And so it's proportional to the log. So the span turns out to be order log n total coming from the reduce. Okay, which is to say that this algorithm is quite highly parallelizable because it has a lot of stuff to do. It has to compute all n squared pairs of accelerations, but this map runs in parallel and this map runs in parallel, which means that really you're just doing the like time to do the reduce, which is a tree span, the span of doing a linear time thing on a tree, which is order log n. And so even though there's a lot of stuff to do, a lot of it can be done independently, right? So number one, I can compute the acceleration on each body independently because you're just all independent calculations. And then number two, when I'm doing the addition, I can like do the addition on a tree, compute all the accelerations in parallel, and then do the addition on a tree to only end up with a log span there. Okay, so that's pretty good. However, it's not good enough for some bigger simulations. So what you're going to do in the homework is to look at a better algorithm for doing the same kind of calculation, though it's not going to actually produce the same results as what we did here. Instead, it's going to produce an approximation of these results. And so the thing that you're going to do for homework, the idea of it is that if you've got all of space and you're interested in like, here's a star over here and what's the acceleration on it? Well, if you've got a whole bunch of bodies like over there, then what we're going to do is we're going to approximate all of those bodies by a sort of pseudo planet that lives at the center of mass of all the bodies that we started with over there. And then what you're going to do is you're going to calculate the force on this based on just the interaction with the center of mass rather than doing each of the bodies individually. So if something's too far in a certain sense away from something else, then you kind of group all of these together into one and only do the calculation once rather than doing the calculation with this and 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 so on. Okay, and so this isn't going to give like exactly same answer as before. It's not going to give the right answer, but it's going to give an approximation, which is, hopefully good enough for learning whatever science you're trying to learn out of your simulation. And the technique that we'll use to do this is basically we're going to recursively divide space up into quadrants. And then when a certain quadrant is, we'll keep track for each, unit of space of all of the things in that quadrant. And then when a certain quadrant is, we'll keep track of all the things in a quadrant. We'll keep track of the center of mass, the average kind of average planet of the quadrant. And then once things get too far away for some threshold parameter that determines when things are too far, what we'll do is we'll compute the acceleration not based on like everybody in the quadrant, but just based on the center of mass there. Okay, so this is called the Barnes-Hutt algorithm for approximating n-body simulation, named after the people Barnes and Hutt who came up with it. And it's going to be a nice example of both sequence parallelism like we saw with the accelerations code from before, and also tree parallelism because we're going to recursively divide up space into a tree of quadrants there. Okay, so you can have a look at that in the homework. Okay, talk to you all later.